Okay, next up we are going to talk about enthalpy. I've already briefly mentioned this. Enthalpy is H, okay, and it is basically chemical energy. So the key here is that we don't usually care about P delta V work. We don't usually care how much work a reaction does. We really just care about how much energy, how much heat is released. Like for instance, during a combustion reaction, we want to know how much heat is released. So that's why we usually use enthalpy in chemistry. Very rarely do we talk about internal energy, although it is hugely important. Enthalpy just comes up a lot more. So the definition of enthalpy, H is equal to E plus PV. Okay, and that's internal energy plus work. Now, at constant pressure, I'm sorry, this is not work. I misspoke when I said that was work. That's just pressure times volume. We don't have work until we have a change in volume. So at constant pressure, which is to say a bench top, so if you were to actually do the lab today or this week, it would be in a coffee cup, and a coffee cup is open to the atmosphere. Atmosphere has constant pressure, not day to day necessarily, but while you're doing your reaction, the pressure is constant. So what we can do is we can say change in enthalpy is equal to change in internal energy plus constant pressure, so there's no change there, times delta V. Now we have work. Okay? And if we remember that delta E is equal to Q plus W, we can make a substitution there. And so we get delta H is equal to Q plus W plus P delta V. And now we can also say that P delta V is equal to negative work, because work is negative P delta V. Make that substitution, we get delta H is equal to Q plus work minus work. So obviously that just means that the work goes away. So we get delta H is equal to Q sub P. And that sub P just means constant pressure, heat at constant pressure. So that would be the kind of thing we would have in a normal lab setting, like I already mentioned. Okay, so let's talk about heat for a second and a couple terms associated with heat flow. One is endothermic. Many of you are probably already familiar with this, and I believe I mentioned it. This is simply a process that absorbs heat. And if you want a way to remember it, it absorbs heat, so heat enters the system. Endothermic starts with EN, enter starts with EN. All right, if it heat process that absorbs heat, so that means delta H is greater than 0. And that just means that it's a positive value. Okay, so a simple example of that would be H2O liquid going to H2O gas. Now we can all reason out that vaporizing liquid water to gas takes some energy. And the delta H for this reaction is 40.7 kilojoules. Now the opposite of endothermic, you probably know, or may know I should say, exothermic. And this is a process, and when I say a process, It can mean a chemical reaction, or up above here, the water going to gaseous water. There's no reaction occurring, but it's still a process that involves heat. So this is a process that gives off heat. Okay, so that means delta H is less than 0. This is just another way to say it's negative. Okay, so chemical reaction that shows that. I'm going to make it real complicated. H2O gas goes to H2O liquid. So it may not be totally obvious, but when gaseous water turns into liquid water, it gives off energy. How much energy? Well, delta H is, go ahead and guess. Hopefully you said negative 40.7 kilojoules. Notice it's just the opposite of the value above. You flip a reaction around and you change the sign of delta H. That'll come up in a little bit. Okay, that'll be really important. But that is a very, very simple process. The vaporization of water. I'm sorry, the condensation of water, and it gives off negative 40.7 kilojoules per mole of water. Because remember, we have little coefficients out in front of here. These are all 1 mole. Okay. Let's just do one really simple example using those. What is the energy change associated if 10.0 grams of water at 100 degrees Celsius, and that's important because this is the boiling point of water. We'll worry more about what that means in a couple chapters. Vaporizes. So we have our reaction already up there, but we can just rewrite it. H2O liquid goes to H2O gas, and delta H is equal to 40.7 kilojoules. Okay, so in order to do this problem, we're given 10.0 grams of H2O. We want to get that to moles, so 1 mole of H2O per 18.02 grams of H2O. And now what's our next term? What's the next term going to be? Well, we want to get that heat, so 40.7 kilojoules. And this is, like I said, per 1 mole of water. So this is a little bit like a mole ratio. Anytime you have a chemical reaction, it doesn't matter what the coefficient is out here, you can just take that delta H and put it over however many moles of whatever you're looking at. So if this, for instance, were 2, not that it is, but it would be 40.7 kilojoules per 2 moles of H2O, but it's not. And we come out with 22.6 kilojoules. And because this is a positive value, this is endothermic. So heat was absorbed. All right, we're going to do more with enthalpy, actually for the rest of the chapter.